Topic 18.2 is delving more into complex calculations with acids and bases. We are returning back to the ionization of water. And if you remember, the water constant, right, is Kw equals the concentration of hydrogen times the concentration of hydroxide ions. And that Kw at standard temperature, so 298 Kelvin, is always 1.00 times 10 to the negative 14. And that is why, like, when we have a pH of 7, we have equal number of hydroxide and hydrogen ion concentrations. What we're going to be adding on to now is the understanding that because it is a constant, right, just like it's an equilibrium constant, it is temperature dependent. So just like Kc, just like the K in rate, all those Ks mean temperature affects the constant, and this is no difference with your Kw. And so when you go through and you look at the ionization of water, and it's an equilibrium reaction, so we have waters breaking down into hydrogen and hydroxide ions. This is an endothermic process in the forward direction because it is breaking bonds. It's breaking the interaction between a hydrogen and its hydroxide ion. Therefore, understanding that is an equilibrium reaction and it's endothermic, we can predict the effect that temperature has on the Kw value, right? So if we increase temp, so we're increasing the temperature. Increasing temperature favors the endothermic process, and in this instance, that is the forward reaction. So that means we are going to make more product, and that means your Kw is going to increase in value. If you decrease your temp, that means it favors your exothermic process, and for this reaction, that is in the reverse direction. So that means we're going to have more of our reactant or full water, and which means your Kw is going to decrease. And so understanding this relationship, when we go to dissolve compounds and ionic salts and even running acid-base reactions, because those all have to be aqueous, we need to understand what's going to happen based off the temperature and the dissociation of water in addition to the acids and the bases, which is why you will always be given a temperature in which these reactions are running. So if we change the Kw value, you're going to change your hydrogen and hydroxide ion concentration as well. And that means you're going to change the pH, right? And so if it's no longer 1.00 times 10 to the negative 14 as its standard, it may then change what H and OH looks like for a neutral pH. So here's a series of just calculations going through and looking at the change in temperature, right? And so we can start with 0 and we're going up to 50 degrees Celsius. And so you can see how the K value changes, right? Because we said in decreasing temperature favors your reactants, which means your Kw decreases. And so here we have to the negative 15th, and then we have going up to the negative 14th, right? And if you look at your hydrogen ion concentration, but it may be easier to look at your pH. So at 0 degrees Celsius, 7.47 is actually the neutral value, so it's slightly above 7. Whereas when you're at 50 degrees Celsius, 6.63 is your neutral value. And so even though the pH changes, water is still neutral. It's just your neutral point because your hydrogen and hydroxide ions are always going to equal as long as it's just water ionizing. And so you need to understand the temperature in which you're running your reactions at in order to determine what is the ionization of water, to truly know where your neutral point is going to occur, and that will therefore affect where an acid or base titration may take place, because it may not be exactly where we expect due to the ionization at different temperatures. So now we're coming back to the pH and pOH scales. All right, they are interrelated. So if you have And these are calculations we've talked about before, sorry. So remember, to find your pH, you're going to do the negative log of your hydrogen ion. Well, so POH is going to be the negative log of your hydroxide ion. No different. If you know, or you're looking for your hydrogen ion concentration, it's 10 to the negative pH. Well, if you want to know your hydroxide ion concentration, it's going to be 10 to the negative POH. So the calculations are the same. We're just looking either at hydrogen ion concentrations or hydroxide ion concentrations. So they have an inverse relationship, as we have seen with the ionization of water. If you're going to increase your hydrogen ion concentration, you're going to decrease your hydroxide ion concentration due to the ionization or the water constant calculation. And so we've talked about that in the SL portion as well. We're just reiterating it here. And the scales are also inverse. All right. So that means if we look specifically at hydrogen, if we increase your hydrogen ion concentration, you decrease the pH value, or the closer to 0 it gets. Well, it's vice versa for your OH ions, right? So if you increase your hydroxide ion concentration, you're going to decrease the POH value for it. Now, as I'd mentioned over here with our water constant, and we understand that, so what's really cool is we can take the logarithm of, we can essentially take the pKw, and so that's going to be the negative log of 1.0 times 10 to the negative 14. And so that means that pKw can equal pH plus POH. And they're just so much more simple numbers to work with than negative exponents. So that means that when you take the negative log of 1.0 times 10 to the negative 14, you get 14. And so it makes a very simple calculation of saying pH plus POH equals 14. And so we don't have to worry about the ion concentrations. We can just work with whole values that represent those ion concentrations. And it just makes it a little bit easier to understand. And so here, sorry I have the writing going over it, but you can see that the scales, again, they're inverse of each other. So we have our hydroxide ion, or sorry, our hydrogen ion concentration on top and our hydroxide ion concentration on the bottom. And so pH goes from 0 to 14, POH goes from 14 to 0. They're inverse of each other, which is why we can actually put them on one scale of 0 to 7 and then 7 to 14 to look at H and OH. But never do they equal 0. You'll always have some hydrogen and some hydroxide ions. It's just the ratio in which they are at that will predict an acid or a base solution. And this graphic is just really neat in how it kind of summarizes it all together. And so here you have our hydrogen ions. So with our pH, we can calculate our H. If we know our H, we can calculate our pH. Going all the way over to the right, if we know our POH, we can figure out our OH. If we know our OH, we can figure out our POH. And then they interact in the middle because we have hydrogen and we have hydroxide. And so if we know our hydrogen and we know our Kw, we can find hydroxide. If we know our hydroxide and we know our Kw, you can know your hydrogen. And we always know that Kw is going to be 1.0 times 10 to the negative 14 at 298 Kelvin. But again, what's beautiful is the fact that they all interact. And so pH, POH equals pKw, and now we don't have to worry about working with hydrogen ion, hydroxide ion concentrations. So here we're going to work an example of how we can use all these calculations together. So if we have lemon juice, and we know it has a pH of 2.90 at 298 Kelvin, so standard temperature. Well, if we know our pH, that means we can find our hydrogen ion concentration by taking 10 to the negative pH. So that means 10 to the negative 2.90 gives us 1.26 times 10 to the negative 3 moles per decimeter cubed. Because we know our pH and it's occurring at standard temperatures, we can figure out what our pOH is. And so if we isolate pOH equals 14 minus pH, so that is 14 minus 2.90, that's going to be 11.10. I'm going to square these so we can keep track of all of them. So now that we know our pOH, we can find our OH ion concentration by taking 10 to the negative pOH. So that means 10 to the negative 11.10, and that's going to give you 7.94 times 10 to the negative 12 moles per decimeter cubed. Or, because you know Kw equals hydrogen ion concentration and hydroxide ion concentration, you can take 1.00 times 10 to the negative 14 equals 1.26 times 10 to the negative 3 times your hydroxide ion concentration, and guess what? You're going to get the same number. What a concept, right? So there's lots of different ways you can solve for all this information. Now, is this, and if you didn't even know, you could determine if this is an acidic or basic solution by looking at the concentration of hydrogen ions to hydroxide ions, which we had to do in the SL portion. So because there's a lot more pH or hydrogen ion concentrations to hydroxide ion concentrations, you have an extremely basic solution. Sorry, acidic solution. Oh my goodness. So if you have now looking at how we can do this with solution calculations. So looking at strong acid and base. What's nice is your pH and pOH can be deduced from your initial concentration. And that's because we can assume full dissociation, which means the concentration you have initially equals the concentration you're going to have at equilibrium within the reaction. So let's look at a base and then we'll look at an acid. So if we have the dissociation of sodium hydroxide, it's going to fully dissociate into sodium ions and hydroxide ions. If you have your initial concentration at 0.10, we can ignore the change because this change is going to be the same. We assume full dissociation, right? So that means we should have no sodium hydroxide left over. And that means that should all go to our sodium and our hydroxide ion concentrations. Well, I really don't care about the sodium, right? I really only care about that hydroxide because that is what makes it a base. So therefore, what is the pH of this system? So if we have pOH equals the negative log of your hydroxide ion concentration, right? So we take the negative log of 0.10 and you get 1. And so that's going to be your OH concentration. So what's the pH of the solution? Because that's what we can actually directly measure. We don't actually have pOH meters, we only have pH meters. So what would be the pH of the solution? Well, we know that pOH plus pH equals 14. So 14 minus 1, pH of 13. So we have a strongly basic solution. Okay, so let's look at an acid. So if we take sulfuric acid, which is a strong acid, and it fully dissociates, this dissociates into 2 hydrogen ions and sulfate ions. So if we initially have 0.15 moles per decimeter cubed of sulfuric acid, and because it's strong, we assume complete dissociation, so we should have no sulfuric acid remaining. And we're going to have 2 times 0.15 hydrogen ions and 0.15 sulfate ions. Again, we only care about the hydrogen because that's what makes it acidic. So then we can take the pH And remember, 2 times 0.15 is going to be 0.30. And that's going to give you a pH of 0.52, an extremely acidic solution. And so you could do the same thing for hydrochloric acid or nitric acid, and you're going to see that sulfuric acid is stronger than the other two because it releases 2 protons per compound that it dissociates into. What about weak acids and bases? Well, as we saw from 8.4, weak acids and bases do not fully dissociate, which means they come to an equilibrium point, which means we have to write an equilibrium expression. And then we use that expression in order to determine what is that hydrogen ion and hydroxide ion concentration. So if we have, looking at an acid first, so we have our Bronsted-Lowry acid, and we're going to dissociate it in water. So it's going to give off a proton, and we're going to make hydronium, or you could just write H+. It doesn't really matter. And so we have this equilibrium reaction. Well, just like with the Kw, we can ignore water because it's a constant, right? So we're going to ignore water because it is there, it is constant, and Kw is taking that into account. So that means we have Ka, which is your acid dissociation constant, equals either H+ or H3O+, they're the same thing, times A-, which is your ion, over the concentration of your original parent acid. So this is what we consider a modified equilibrium constant or expression because we took away the water, because water is part of Kw. And this is, Ka is called the acid dissociation constant. And the Ka is what's going to give you a measure of dissociation. So how strong is your weak acid in this instance? Now, the Ka does not depend on the concentration of the parent acid, because you can have a 0.1 mole solution of hydrochloric acid and a 0.1 mole solution of acetic acid. Acetic does not fully dissociate, so even though it's the same concentration, it's not going to be of the same strength. And that Ka is going to be a fixed value for a particular acid at a specified temperature. And you have that in table, I believe, 21 in your data booklet. And just like understanding equilibrium expressions again, so if you're going to increase your Ka, you are creating a stronger acid, because the way you're going to get a bigger Ka is to have more concentration on top of the expression divided by a smaller value, therefore increasing Ka. So that is a direct measurement of your strength and how much dissociation is going to occur. So we can do the same thing for a base, right? So if we have our base and we're putting it into water, water is going to act like the acid, and it's going to donate a hydrogen to our base because base has a lone electron pair to accept it, and it's going to release a hydroxide ion. So just, again, because Kw is present, we can ignore water as a constant. So that means Kb equals your conjugate acid times your hydroxide ion over the original base. And that is the base dissociation constant. Just like with Ka, it is a fixed value for a particular base at a specified temperature. It is also a measure of the dissociation and therefore strength of the base. So the more dissociation you have, the larger your Kb value is going to be. It's just looking at hydroxide ion concentration versus hydrogen ion concentration release. So Ka and Kb allow the ability to compare the strengths of weak acids and weak bases. Allows us to calculate the ion concentration at equilibrium, because guess what? We are going to have to set up an equilibrium equation. Therefore, we have to have our ice table in order to figure out our ion concentration. And we could either determine our pH or pOH, or we could actually be given our pH and pOH and work backwards. So there's a lot of different ways that we can go through and solve information. So as I mentioned, we're going to have to set up an ice table. So you need to remember that you're going to be given an initial concentration. That initial concentration is prior to any dissociation that may occur. If you're given your pH or pOH in the information prior to working your problem, that is the hydrogen ion or hydroxide ion concentration at equilibrium, which means you can then go back and find out what that change is going to be from your initial concentration. Again, just like with your equilibrium calculations, it's the equilibrium concentration that's going to go into your Ka or your Kb calculation. And because we're working with acids and bases, we're typically working with very small Ka and Kb values. In which case, if you're given your Ka or your Kb value, you're going to assume very little dissociation is occurring, and therefore the initial concentration of your acid or base is going to be the same as your equilibrium concentration. Same exact setup as we saw in topic 17. All right, so we're going to work an example of what does this look like. So calculate your Ka. At 298 Kelvin for a 0.01 mole per decimeter cubed solution of ethanoic acid. It has a pH of 3.4 at this temperature. All right, so I go through and I'm going to set up my rice table. So looking at the dissociation, so CH3, COOH, we have water, and so therefore we're going to have CH3, COO minus, and your hydrogen ion or hydronium ion concentration. All right, so we know our initial is 0.01. We do not care about water, so I'm just going to draw a big X through that section because it's part of the KW. All right, and then this was before dissociation, therefore our ions are not present as of yet. All right, where do we go from here? We are given a pH. So that means this can give us our hydrogen ion concentration at equilibrium. Well, then how do I find that? Lucky for us, we have a calculation. 10 to the negative pH, right? So we want to take 10 to the negative 3.4, and that is going to give us 4.0 times 10 to the negative 4. So that is what it becomes at our equilibrium. So we have 4.0 times 10 to the negative 4, which means that's what we had to change by. And because it's a 1-to-1 ratio, our ion is also 4.0 times 10 to the negative 4. So we need to subtract that 4.0 times 10 to the negative 4 from our original acid, and we get 0.01 minus 4.0 times 10 to the negative 4. So based on our sig figs, it's 0.01, and that is showing you that we can assume the initial concentration is going to be the same based off what we can measure and the precision of the data we're given. Set up your Ka expression. Plug in your values. And because your two ion concentrations are the same, we can just square it. and we get a Ka of 1.6 times 10 to the negative fifth. And there's your answer. And then if you were given a variety of different weak acids and you had their Ka values, you can rank them based off strength to how close you are to the value of number 1. Because we have nothing to compare this to, we can't necessarily say it's weaker or stronger. We would need other values to compare it against. So you'd set up a Kb calculation exactly the same, but I want to do a different kind of calculation. We have to calculation of your hydrogen ion concentration and pH, or your hydroxide ion concentration and your pOH from a Ka or Kb. I'd like to do a hydroxide or a base because we did an acid in the prior problem. So if you have a 0.20, I can not write well, 0.20 mole per decimeter cubed solution of NH3. You know your Kb is 1.8 times 10 to the negative fifth at 298 Kelvin. What is the pH? Oh boy, that's a lot of steps. Okay, so setting up my rice table. So we have our dissociation of NH3. So we have NH3 being put into water, and it's going to dissociate into NH4 plus and OH minus. You know our initial concentration is 0.20 moles per decimeter cubed of our base, so ammonia. And because this is before dissociation, we have none of our ions present, and we ignore water because it is a constant. We are not given pOH, which means we do not have our equilibrium concentration. Therefore, because we're given the Kb and it's such a small value, we have to solve for x. So that means we have a change of x. And so our value of our ammonium and our hydroxide ions are x. Because it's such a small value for our Kb, we can assume very little dissociation based off the sig figs we are given in our problem. And so our initial concentration is proportional or approximate to our equilibrium concentration. All right, so now we're going to set up our Kb expression. Okay, now plug and chug. So we get x squared because they're the same value over 0.20, and that equals our Kb. And so you can go through and solve for x. So I'm going to just move over. So x is the square root of 1.858 times 10 to the negative fifth times 0.20. And that's going to be 1.9 times 10 to the negative 3. And so there's x. And that means that is our hydroxide ion concentration. But that's not what we're asking. We're asking for our pH. Okay. So you can solve it one of two ways, depending on what you want to do. You can then take the negative log, so pOH, pOH equals the negative log of 1.9 times 10 to the negative 3, and that's going to give you 2.72. Because this is happening at 298 Kelvin, we can then take our pH plus our pOH equals 14. So pH equals 14 minus 2.72, and that's going to give you 11.28. And that's your answer. Another way you could have solved that, because you know your hydroxide ion concentration, you could have taken 1.0 times 10 to the negative 14 equals your hydrogen ion concentration times your hydroxide ion concentration. I'm not writing very well. And then take the negative log of your hydrogen ion concentration, and you would have gotten the same number. So you pick the method you like and go with that method. whatever it is you're most comfortable with. So due to the really small numbers for the Ka and the Kb value, a lot of times they'll be turned into a pKa or pKb value, just like pH and pOH, and it makes it just easier to work with, just because they're more of whole numbers than the negative exponents. So just like pH and pOH, you have your pKa equals the negative log of your Ka. So your pKb equals the negative log of your Kb. And vice versa, your Ka equals 10 to the negative pKa, and your Kb equals 10 to the negative pKb. Just like with pH and pOH, pKa and pKb are usually positive and they have no units because they're just representing the extent of dissociation with your acids or bases. They have an inverse relationship. So if you have a strong acid, your pKa is going to increase towards your weak acid. Your Ka increases towards your strong acid. Because Ka is a representation of dissociation, the lower your pKa value, the higher your dissociation is because of your Ka, so on and so forth. Just like with pH and pOH, a change of one value of your pKa or pKb has a tenfold change in your Ka or Kb. It's no different. It's just adding in Ka versus just H and OH. So there's a unique relationship you can have when you have your conjugate acid and base pairs. So the Ka of, let's just say, your parent acid times your conjugate acid times your Kb of your conjugate base. That is the same thing as saying your hydrogen ion concentration times your hydroxide ion concentration equals Kw. So essentially, this is for your conjugate acid-base pair. For an acid-base pair, your Ka times Kb equals your Kw. And the reason this works is if you have your Ka times your Kb of your conjugate acid-base pair. So that means if you have your Ka, so your acid dissociates into the proton and the ion, and then you have your acid. And then your conjugate base turns back into its parent acid and releases a hydroxide ion, or goes back to the base, whatever that looks like, and then your ion on the bottom. Well, if you cancel out all the commonalities, what are you left with? Your hydrogen and hydroxide ion concentrations. And so essentially then, we can say for conjugate acid-base pairs, Ka times Kb equals Kw, which means your pKa times your pKb, that was not a K, equals your pKw, which means your pKa plus your pKb equals 14, just like your pH plus your pOH equals 14. And so you can be given, let's say, your pKa value, and then you can find your pKb value, and then you can find your pOH value, because we have all those calculations and we can do it. It's just giving you lots of different ways to work around the information in which you have.